How's it going? Didn't see you there. Welcome. Third video in our 8th unit on kinetics and equilibrium. We're going to talk about potential energy diagrams. And I found the microphone. Turned it on, so hopefully I'm a little louder in the video this time. So, potential energy diagrams. At the conclusion of this little lecture, you should be able to identify some of the basic information held within a potential energy diagram. What it is, and all the stuff, all the little parts that we're going to be labeling are the important parts for today. Okay, so here's our little leading. Chemical reactions happen, duh. But is there a way to chart their progress, like in a graphical manner? Okay, we chart our progress on the unit by doing the checklist on the smartboard here, but is there a way we can chart the progress of a chemical reaction as it goes from the reactant side to the product side? Now, exothermic and endothermic reactions look differently when you graph them out like this. Both types all show certain things though, like heat of reaction, which is how much heat is absorbed or released in the reaction. The forward and reverse reactions, activation energy, and the effect of adding a catalyst. So even though these two graphs are going to look slightly different, all of the information, like heat of reaction, forward, reverse, all that stuff, is in both types of diagram. So let's get to it. In our lecture notes pack, first thing you got to know about is potential energy diagrams. We've talked about bonds having stored energy, potential energy. And that reason chemists use diagrams called potential energy diagrams to illustrate the potential or stored energy changes that occur during specific chemical reactions. Okay, so if we're talking about the potential energy of bonds, we're talking about that stick right there. And if we are talking about reactions, the breaking and reforming of bonds, let's imagine that we want to take A and B, we're going to break it apart, okay, and form new bonds to make, like C and D. Get in there. Had to do my collision theory properly. Orientation and energy. So now we got something else. So A and B, if I wanted to react it, you had to break the bond first, and then you had to form new bonds to make the products. So the making and breaking of bonds is tracked in this graphical method in a potential energy diagram. And bonds take energy to break and release energy when they form. So energy changes during a reaction. So the heat of reaction is the amount of heat energy lost or gained throughout a reaction. Delta H is something we call enthalpy. Enthalpy, it's got an H in it. Delta H, enthalpy, it's heat. So the change in heat of the reaction. The potential energy of the products minus the potential energy of the reactant. So here's a good equation that you will not find on table T. So you got to kind of memorize this one. Delta H is the heat of the product portion of the equation minus the heat of the reactants portion of the equation. So how much heat the products have, you take away the heat that the reactants had, and you find how much the heat changed by. Recall there are two types of reactions. Reactions that release energy. Energy goes out, it exits, it's exothermic. And delta H's for those type of reactions have a negative value to show the loss of heat. Energy released is shown on the right-hand side of an equation in that case. Okay, so this is an exothermic reaction. There's two ways to see it. Either delta H is negative, and it's listed for you, or you see energy as a product of the reaction. Example, sodium in water. Lots of heat and fire produced as a product. Heat felt on a test tube during a reaction. So you feel a test tube, it feels hot. Reaction is exothermic and energy is being produced. Delta H, the heat of the enthalpy of the reaction, would be a negative value. Reactions that absorb or gain energy are called endothermic reactions. The heat enters the system. Delta H in this case is a positive value, and energy is going to be on the reactant side of the equation, on the left. Now, an example of this would be baking. You need the oven to supply the heat. If you mix all your ingredients, A plus B plus C plus D, and all that stuff you put in the pan, you have to add heat, the other ingredient, to make your cake happen. So baking, cooking, anything where you heat something up is technically an endothermic reaction. You got to heat it up to make it happen. It's technically considered an endothermic. If it happens spontaneously and releases a bunch of heat, that's exothermic. Okay, so that's the difference between endo and exo. let's look at table I. So table I is all about showing you what the heat of the reaction is in a numerical form. We'll get to the graphical portion in a little bit. So on table I, I'll have to get a table I, reference table I. What I'm going to do is I'm going to look up what the delta H value for the reaction is. So I'm playing the matching game. I see N2 plus 2O2 makes 2NO2 gas. So I'm just going to find that reaction here. N2 gas plus O2 gas makes 2NO2 gas. There it is. And it says it's positive 66.4 kilojoules per mole. So in order to determine endo or exo, all I got to look at is the sign out front. If the sign is positive, heat is entering. So that's endothermic reaction. Now I'll play the matching game again. N2 gas plus 3H2 gas makes 2NH3 gas. So N2 gas plus 3H2 gas makes 2NH3 gas. Yep, there's the reaction. Value here is negative 91.8 kilojoules per mole. So that's how much heat is involved in the reaction, and the sign out front tells you if it's being released or absorbed. And the negative sign means that it's being lost, so it would be exothermic. That's all there is to this stuff. Okay, so I want you to try number 3 by getting your reference table I and completing that one yourself. And remember, the thing you're looking for is to see if the sign is positive or negative, because that translates into endo or exo. Let's check out some forward and reverse reaction stuff. So reading left to right is how we've been doing it all along. So left-hand side, we've got our reactants, R, and right-hand side, we've got our products. The forward reaction is one arrow that points to the right. That's it. Go. A plus B makes C plus D. Boom, done. Reverse reaction is when we have forced the reaction to go backwards. And we're going to start to see this happen in potential energy diagrams and equilibrium. So we're forcing the reaction to come back the other way. You could technically rewrite the entire equation, flip it backwards, or you could point the arrow in the other direction. Okay? Now, activation energy. If I want A and B to come together, I need to hit them with the amount of energy to get a reaction to occur. That's where we're talking about with the, got my molecule, collision theory. Okay? I want them to come together. I have to get them together with the right amount of energy. So, you must get over the bump in order for a reaction to be successful. If I want this to happen, I got to get them to come together with the right amount of activation energy for it not to come apart. All right? So let's check out what a basic potential energy diagram looks like. I want you to relabel this because it's not great. So it's called energy. There. Potential energy, technically. Potential energy on the y-axis. And this often called is the reaction coordinate. It really just means time. Okay? And so we have on the left side, we've got our reactants, which you'll often see as things like A plus B, or something like, you know, CH4 plus O2. So the reactants involved. On the right-hand side, we have our products. In this case, if we're doing A plus B, we're probably making something like C, or our products of methane burning would be H2O plus CO2, something else like that. And this big hump in the middle, that represents the arrow that happens during the reaction. At the very top, tippity top, we have the activated complex. And the amount of energy it takes to get from the reactants to the top. So this arrow right here is the activation energy. Alright? And the last thing we're going to talk about is how a catalyst shortens the reaction time needed. So this catalyst here, if we add the catalyst, the amount of activation energy changes. So it's like the policeman directing traffic reduces everybody's stress level, but you still get from where you wanted to, from where you're coming from to where you're going to. It's just the amount of energy in the transfer, in the movement, lowers so it can happen quicker, more efficiently. A catalyst shortens the reaction time needed for reaction to complete because the catalyst takes the activated complex and lowers the amount of energy. So normally we'd have to go up over this big hump, like a big roller coaster, but the catalyst lowers the height of that roller coaster. Now, at the very end here, lowers the activation energy needed for the reaction to get started. It gets the reaction started easier and makes the reaction complete itself faster. So that's what the important parts of potential energy diagram are. We're going to do a lot more practice on this. So at this point, you should have a basic understanding of what a potential energy diagram is. The products and reactants side of it, the activation energy portion of it, and you should be able to use table I to determine if something is exothermic or endothermic just by looking at the sign for delta H. There's no practice pages specifically on this material, but there's a bunch after our next lecture. So thanks for watching. Talk to you later.